Can you see my screen? Can all of you see my screen?
Yes, ma'am.
Okay. Okay, so in our last class, we had started the discussion on gradient, which was the first of the three differential vector differential operators that we are going to discuss. And we had said, we had seen how we can take the gradient of a scalar and why when we And we saw that why when we take the gradient, scalar is converted into a vector. We saw what a directional derivative is. And we also did some problems in which we saw how to find out the directional derivative of a given scalar function. Okay. Now the other significance of the gradient operator Okay. The other significance of the gradient operator is the geometrical significance. Okay, so in our last class we saw the physical significance. The other significance is the geometrical significance. What happens is, suppose we have an equation like this, where we have some scalar function which is a function of x, y and z equal to a constant. Okay, so this equation usually is that of a surface. For example, if it is like this, ax plus by plus cz equal to constant, then it is the equation of a plane, or it can be the equation of a sphere like this, x square plus y square plus z square equal to c. So such an equation, phi equal to constant, can represent the equation of a surface, any three-dimensional surface. Now if since phi equal to constant, therefore d phi is equal to 0. Okay, so from our definition of partial derivatives, we saw that if phi is equal to phi of x, y, z, then d phi can be written as del phi del x dx plus del phi del y dy plus del phi del z dz. Okay, so it implies that since d phi is 0, therefore this function on the right hand side is equal to 0. So what we do is we write this function as the dot product of two vectors in this manner. Del phi del x I cap plus del phi del y j cap plus del phi del z k cap dotted with dx I cap plus dy j cap plus dz k cap equal to 0, which means this term within the first of the bracket, the first term here on the left hand side, is nothing but grad phi, and the second term here is nothing but dr. So what we get is grad phi dot dr equal to 0. Okay, so the dot product of these two vectors is 0. Now for any given surface, if r is the position vector, then dr, the vector dr, will always lie on the surface. R is a variable vector, depends on at which point on the surface you are taking it, but wherever you take it, it will always lie on the surface. And the fact that grad phi dot dr equal to 0, it means that grad phi is always perpendicular to dr, which means that grad phi is a vector normal to the given surface at the specified position. Okay, so whenever you are given the equation of a surface and asked to find its normal, then what you have to do is you have to find the gradient of the given function. Okay, so we'll do two problems to show what I was trying to say. First of all, find the unit normal to the surface x square y plus 2xz equal to 4 at the point 2, minus 2, 3. Okay, so what are we going to do? First step is, this is the function, so identify the surface first and therefore identify the function phi. Then find out grad phi. So you know how to find out grad phi if we have followed my previous class. So grad phi is 2xy plus 2z I cap plus x square j cap plus 2x k cap. Okay. So at the point 2 minus 2 3, you substitute the values of x, y and z by 2 minus 2 3. So what you get is the vector minus 2 I cap plus 4 j cap plus 4 k cap. So this basically gives you the normal at the given position on the given surface. However, the problem has asked us to find out the unit normal. So what we'll do is we'll find the unit vector along this vector that we have obtained grad phi. So unit vector is grad phi divided by mod grad phi, which comes out to be this. Okay. Just keep in mind that this plus minus sign is very important. When you are taking the root of this vector, it means root 36 is equal to plus or minus 6. Okay, so don't forget to keep the plus and minus sign. Just don't write only 6. You know why? Because at any point on a surface, there are two normals always. One is the outward normal and the other is the inward normal, or upward normal and downward normal. Okay, so plus and minus sign indicates that behavior, that any surface at a given point has two normals, because any surface is double-sided, so it has two normals on both the sides at a given point. So if you don't give the plus minus sign, the examiner might deduct a few marks, because it indicates that you don't know that a particular surface is two-sided and always has two normals. So whenever you are given such a problem, always give the plus and minus sign in front. Okay. So this is one kind of problem. The other problem is like this. Find the angle between the surfaces x square plus y square plus z square equal to 9 and z equal to x square plus y square minus 3 at the point 2 minus 1 2. Okay, so what is happening here? There are two surfaces, and obviously the two surfaces are intersecting along a line. On that line, you have been given a point where you are asked to find the angle between the two surfaces. So since the two surfaces are making an angle, obviously they are intersecting. So you have to find the angle between them at that point. So what will you do? You will quickly find the normal to these two surfaces. The angle between the surfaces will be equal to the angle between the normals. Okay. So first identify the surfaces. This is phi 1 and this is phi 2. Next find the gradients. Grad phi 1 at 2 minus 1 2 is this, 4 I cap minus 2 j cap plus 4 k cap. And grad phi 2 at 2 minus 1 2 at the same point is 4 I cap minus 2 j cap minus k cap. Okay. So next what do? You have to find the angle between these two vectors. So that is a simple dot product problem. So grad phi 1 dot grad phi 2 is mod grad phi 1 into mod grad phi 2 into cos theta. So you do the dot product, the direct dot product, the component form on the left hand side. So you have 4 4s are 16 plus 2 2s are 4 plus 4 1s are 4 minus, and on this side you have modulus of this is root 36, modulus of this is root 21 into cosine of theta. So you have theta is cos inverse 16 divided by 6 root 21. Okay, so this is the required angle between the surfaces at this particular point. These are some typical problems that you might get from gradients. So we did some problems involving the directional derivative and the normal gradient of a given function of r. Remember, we derived a formula, and the other form is from the geometrical significance. So these are the typical problems that you can get. You can get more problems in any other mathematical methods book from the chapter of vector analysis, the gradient portion. You can get problems. Please look through, or you can see university question papers, and please look through the problems and solve them, because you do get problems from this part. Okay. Next we will study the divergence. We studied the gradient. Now we will study the second operator, which is the divergence of a vector. Okay. V is a vector field of this form. Of course, it's a function of x, y, and z, and components v1, v2, and v3 will also be functions of x, y, and z. Then, if such a field is defined, of course, and differentiable at each point x, y, z in a certain region of space, then the divergence of this vector field is defined in this manner. Okay, divergence of V is, you write down the expression of the del operator, the vector differential operator, dotted with, you write down the expression of this vector in component form, and therefore you get divergence of V equal to del V1 del x plus del V2 del y plus del V3 del z. Okay, so that is the divergence of a vector. So, for example, if this is a vector function 2x square y I cap minus x y cube z j cap plus z to the power 4 k cap, then this is the divergence. Okay, this is even simpler because you need to take the x component of only the first term, the x derivative of only the first component, y derivative of only the second component, and z derivative of only the third component. Okay, so the first component x derivative gives you 4xy, derivative of second component gives you 3xy square z, and z derivative of third component gives you 4z cube. Keep in mind, do not write down I cap, j cap, k cap here because you are taking the dot product, so the result is a scalar. Okay, this is a very common mistake that people make when they are asked to take the gradient of a scalar. They often forget to give the vector sign or write down the I, j, and k caps, the unit vectors, and when they are asked to write down the divergence of a vector, they often by mistake give the I, j, and k, I cap, j cap, and k cap unit vectors. Okay, so please keep in mind that the gradient is a vector, so you have to give the unit vectors. The divergence is a scalar, so you need not give the unit vectors. Okay, so this is a very common mistake. So just the thing that you have to keep in mind is that the divergence is a scalar and the gradient is a vector. So no unit vectors in the divergence, and you have to give unit vectors in case of a gradient. Okay, so this is a scalar, just keep that in mind. So suppose you are asked to take the divergence of the vector r, where r is equal to x I cap plus y j cap plus z k cap. Can you quickly do this and tell me the answers? Can someone unmute and tell me the answer? What will be the divergence of r? You don't even have to write this down. You can just do it.
I cap plus j cap plus k cap.
Aha, see? No I cap, j cap, k cap. Yes, 3.
1 plus 1, yes.
1 plus 1 plus 1. Yes, 3. Answer is 3. No I cap, j cap, k cap. Yes. Okay, so you learn from your mistake. So I hope you will not make this mistake in future when you do the problems. Okay, so answer is 3. So very simple. I mean, taking the divergence is very simple, and the fact that it's a scalar makes it makes it even simpler. What we'll do is, instead of finding out divergence of different functions of r, using the root over x square plus y square plus z square form, we will directly find the formula for divergence of any function of r, fr, into r vector. Okay, so just a second. Okay, so what we'll do is we'll directly, so even whatever form of fr is given, if you're asked to find the divergence of fr multiplied with the r vector, where r is of course this, then you simply have to derive this formula. Okay, and the same advice goes as I told you in the last class, that if such a problem is given, then you first have to check the marks allotted. If the marks is about 2, 2.5 maybe, then you directly use the formula. If the marks is more than that, then you derive.
Ma'am, can't hear you. Akash Malik muted you, ma'am.
Can you hear me now?
Yes,
Yes, ma'am.
ma'am. Akash Malik muted.
Yes, Akash Malik muted and Akash Malik also left. Anyway, I hope it was by mistake. Okay. So we were trying to find out the general formula for divergence of FR R vector, where R is this. Okay, so divergence of FR R means del del x of Okay, so this means del del x of frx plus del del y of fry plus del del z of frz. All right. So what we'll do is we'll differentiate each of these by parts. Okay. I've written down all the steps, but since I'm not working it out on a board, it is sometimes little difficult to follow. So what you need to do is, after I finish this class, you need to see the PowerPoint and work this out on a pen and paper by yourself, or if you are sitting with a pen and paper, then you can work it out right now as I'm showing the steps. Okay, so divergence of FRR vector. So first we take this term, and if you differentiate it by parts, you take x out and you have del del x of FR, and if you take FR out, you are left with del x, which is 1. Okay, so you get two terms from this first term. One is x del del x of FR plus FR.
Excuse me,
Yes.
ma'am. You have solved by that UV method, ma'am.
UV method, yes, UV method.
Yes.
Each term by UV method, since it's partial differentiation. So each term by UV method. Okay. Okay. Similarly, from the second term, we get. Can you please mute?
Chirag, please mute yourself.
So from second term, we get again 1 FR and y del f del y. And similarly, from the third term, we get FR and z del f del z. Okay. So that's the second step. So what we have, we collect the three FRs independent of the del del x's and del del y's and del del z. So we have 3 FR, and if you look at this term here, okay, x del f del x, which I have written down as x df dr into del r del x. Okay, so I have put a del r on top and bottom. Okay, so basically I've multiplied and divided by del r, but since f is a function of r, I keep df dr, whereas since r is a function of x, y and z, I maintain the partial derivative. Okay, so this is from the first term, x df dr into del r del x plus y. Please, can you mute yourself? I don't think anyone likes the noise that whoever is unmuted is creating. Okay, from this y term here, we have y df dr into del r del y. And from this third term here, we have z df dr into del r del z. Okay, so we have now 3 FR term independent, and these three we have to solve. So 3 FR, we take df dr common from these three terms. So inside we are left with x del r del x plus y del r del y plus z del r del z. All right. So again 3FR and DFD are outside. So inside we have x del x of r, which means del x of root over x square plus y square plus z square, plus y into del y of similarly x square plus y square plus z square root, and z del z of x square plus y square plus z square root. All right. So partially you have to take the derivative of this term root over x square plus y square plus z square. So what will you get? Again 3FR and DFDR are still there. From this term here you get x. This gives you half into 2x into 1 by root over x square plus y square plus z square. Similarly, this term gives you y into half into 2y into 1 by root over x square plus y square plus z square. And the third term gives you z half into 2z 1 by root over x square plus y square plus z square. Okay. So we have 3FR, DFDR, all the 2's cancel out. We have x square, y square and z square, and the same denominator is the same for the 3, so we are left with x square plus y square plus z square in the numerator and root over x square plus y square plus z square in the denominator. Now x square plus y square plus z square, you know, is simply r square, and the denominator here is r. So we have r squared divided by r, so that gives us r. Okay. So the final formula is this 3FR plus f primed r into r. F primed r is simply DFDR. Okay, DFDR is also written as f primed r. So you can see, of course, that is the scalar. There is no vector in the right hand side, and given any form of FR, you can quickly find out divergence of FR vector. Okay, so if I give you now one or two problem, you should be able to use the formula and do it. Okay, so I have not made a slide for them. If I give you the form of FR, you can solve and tell me, and I'll tell you if you are right or wrong. So suppose FR is say r cube. Okay, FR is r cube. Can you quickly tell me what will be the answer if FR is r cube? FR is r cube. Can you solve and someone unmute and tell me what is the answer? Just use the formula. You don't have to do all this. Just put it in this formula here. 3FR plus f primed r, where FR is r cube. Are you trying out? Is someone telling me the answer?
3F plus F dash R square.
What is FR? FR is r cube. So 3r cube plus what is f dash r?
3r square.
F dash r is 3r square. Okay. So you have into r. So you have a 3r cube here, and over here you have a 3r cube. So the answer
6r cube.
is 6r cube. Yes, the answer is 6r cube. One more. FR is log r. FR is log r.
কি হয়েছে?
3 log r plus 1.
3 log r plus 1. Exactly. 3 log r plus 1. F primed r is 1 by r into r. So that gives you 1. So 3 log r plus 1. Okay. So in this manner, you can be given different forms of FR and asked to find the divergence of FR vector. And you simply use this formula and get the answer. If the marks given is 2, if the marks given is 4 or maybe 3, more than 3, then you don't have to do anything. just derive this formula, use these steps to derive this formula, then say this is the general formula. In the given problem, FR is so and so, so the answer is this. Okay. So in that manner, you can do these sums. Okay. Now next we have to go through the physical interpretation of the divergence. The physical interpretation of the divergence is the flux. Okay, so I don't know if you have heard this term flux. You know, whenever there are a lot of particles moving through a very narrow region. Okay, for example, suppose there are dust particles, or there is a fluid moving through a certain capillary tube, or even if there are, say, many people trying to come out through a very narrow opening, then the number of particles per unit area per unit time is called the flux. Okay, so suppose, for example, I tell you that suppose your someone tells you that please meet me in front of the gate of some theater, some movie hall at a certain, say, 6 p.m. Okay, meet me at the gate of this and this so and so movie hall at 6 p.m. You can tell him or her that no, I don't want to go there at 6 p.m. because at 6 p.m. the show ends and the flux of people is very high. So I don't want to face the crowd. So I don't want to go there. What does that mean? It means that when the show breaks, all the people who were inside the movie hall, they all try to come outside in a hurry. Okay, so there are a lot of people coming out through the gates of the movie hall at that particular point of time. So the number of people passing per unit area of the gate per unit time is very high, which means that the flux is very high. Okay, so this is what a flux means, the term flux means. So we'll see how the divergence of a vector is related to this term, the flux. Okay, and now I'll just try to explain the thing. Keep in mind that all this will not come in your exam. I want to just explain the thing to you so that you can understand the physical interpretation of taking the divergence of a vector. Okay, so if you consider a region within a moving fluid, or even if you consider a magnetic field or electric field where you know there are magnetic lines of force or electric lines of force, then suppose v is the velocity of a fluid particle, we write v equal to small v into rho, where rho is the density of the fluid. Okay. So the amount of fluid passing in time t, a unit area A prime, perpendicular to the direction of flow, is the fluid contained in a cylinder of cross-sectional area A prime, which is given by v into t. Okay. So the amount of fluid will be the volume of this cylinder, which is length into area, and multiplied by density will give you the total mass of fluid passing through this particular cylindrical volume. So it is given by Vt A prime into rho. Okay. Now, if you consider another area A, which is inclined to the direction of flow at an angle theta. Okay, so the normal to this area A, this is the normal, it is inclined at an angle theta to the direction of flow. So the amount of fluid which was contained in this cylinder will also pass through this inclined area, inclined surface. Okay, and since this angle is theta, therefore A prime, this is equal to A cos theta. Okay, so this quantity Vt A prime rho, we can replace A prime by A cos theta. So the amount will be given by Vt A rho cos theta. Okay, where we have replaced A prime by A cos theta. Now, the amount of the fluid therefore crossing unit area in unit time is given when you divide this quantity by time and area, because you want unit time and unit area. So it is simply V rho cos theta. Okay. But V rho cos theta is V dot n cap. Okay, because V rho, see here, V rho is V vector and cos theta, where n cap is this normal. So V dot n cap will give you V rho cos theta. All right. So why did I show you this? This I discussed to show you that whenever there is a fluid or a number of particles or a number of lines of force crossing an area, the number of particles crossing per unit area per unit time is given by the velocity vector dot product with the normal to the given surface. Okay. Now, if you consider a volume like this with sides dx, dy and dz inside that fluid through which our liquid or particles or lines of force are moving, then through this volume some amount of fluid is crossing. So either the amount of fluid that moves into this volume is more than the amount of fluid that comes out, or it may be less than the amount of fluid that comes out, or it may be equal. Okay, some amount of fluid enters this volume through the 6 surfaces and some amount of fluid leaves this volume through the 6 surfaces. Okay, now we'll calculate what is the amount that is the difference of the amount of fluid that enters this volume and that leaves this volume. Okay, so suppose we consider this surface here. What is the area of this surface? dz into dy. This is dz and this is dy. This long line over here is the length is dx, width is dx and height is dy. Okay, so consider the fluid coming into this volume through this surface. Okay, so what is it? V dot n cap. Now what is the normal to this surface in the direction of x cap? So the normal is I cap. So V dot I cap is the amount of fluid entering. Okay, so V dot I cap dy dz is the total fluid entering through this area. Per unit area is V dot I cap. So if you multiply it by the total area, you get the total fluid coming in. But V dot I cap, you know, is Vx. So this is equal to Vx dy dz. All right. Now, when the fluid leaves through this surface here, it can be joined by some more fluid from the other surfaces, or the fluid coming out may be less than the fluid entering. We just retain a plus sign. It may be minus also. So it's an algebraic sum. So we say that the amount of fluid that comes out through this second surface facing the x direction is Vx plus delta Vx, where delta Vx is a very small amount. It may be minus or plus. Okay, it may be taken out from Vx or it may be added to Vx. Since delta Vx is very small, we can write delta Vx equal to dVx, and we know that dVx equal to del Vx del x dx. Okay, so the difference in the amount of fluid that enters the volume through the first surface and that leaves the volume through the second surface is given by this. Okay, Vx plus delta Vx minus Vx. So we are left with delta Vx or dVx. So it is given by del Vx del x dx multiplied by the surface area dy dz. Okay. Similarly, the net outflow through top and bottom, that is the y direction, will be given by del Vy del y dy dx dz, and the net outflow through the front and back surface, that is the z direction, is del Vz del z into dz dx dy. Okay, so the net difference in the amount of fluid that enters this volume and that leaves this volume is given by del Vx del x plus del Vy del y plus del Vz del z multiplied by dx dy dz. But this term here del Vx del x plus del Vy del y plus del Vz del z is nothing but divergence of V. So the net difference in the amount of fluid that enters this volume and that leaves this volume is given by divergence of V into dx dy dz. Okay. So this term, the divergence of V, gives us the flux, because if you divide it by the volume of this rectangular parallelepiped here, then you are left with divergence of V. But what it is giving us really is just the amount of fluid crossing per unit area, per unit volume, per unit time, which is nothing but the flux. Okay, so whenever you are talking about the flow of a liquid or particles or lines of force or even people, animals, whatever, you take the divergence of the vector representing their motion in order to get the flux related to this flow. Okay, now divergence of a vector can be greater than 0, can be less than 0, or it can be equal to 0. What does it mean when it is greater than 0? When the divergence of V is greater than 0, it means that the amount of fluid that is coming out from a volume is more than the amount of fluid that entered the volume. How can this happen? Suppose you have a room where there are two doors, one in the front and one in the back. So suppose 10 people entered the room through the back door, and if the number of people coming out through the front door is more than 10, say 15 people are coming out. 10 people entered the room and 15 people are coming out. How can that happen? Only if there is a third door through which more people have entered and joined the 10 people who had entered through the back door. Only then there will be 15 people coming out, whereas 10 people had entered. So there is a source which is adding more particles to the particles which are coming in, so that the number of particles that entered is lesser than the number of particles that are coming out. So divergence V greater than 0 indicates the presence of a source. If divergence V is less than 0, it indicates the presence of a sink. Okay, what does this mean? Suppose again say 10 people had entered the room, but only 5 people are coming out. What does that mean? It means that 5 people have not come out. Okay, so but somehow say that the people cannot stay in the room. Whoever enters have to come out. So there must be a third door through which the remaining people have gone out, so that through the front door only the 5 people are coming out. So the number of people who entered is more than the number of people who are coming out. So there is a sink in the room through which some particles are going before moving out. So the number of particles coming out are less than the number of particles that entered. So divergence V less than 0 indicates the presence of a sink. If divergence V is equal to 0, we say that the vector is solenoidal, so that the number of particles that entered and the number of particles that are coming out are equal. 10 people came into the room, 10 people came out of the room. So divergence is 0. So the flux is always 0. Okay, so the number of people, there are no people added or subtracted. Number of particles are not added or subtracted to the number of particles that entered. It means that indicates that the vector is solenoidal. This has a very, very important, you already know this, okay? Only that maybe you are, this term solenoid, maybe you are listening to it for the first time, but the fact is something that you already know. All of you know that magnetic field is always bipolar, right? If you have a magnet, it always has a north pole and a south pole. You do not get magnetic monopoles. Do you know why? It is because a magnetic field is a solenoidal vector field. Okay, so the flux is always 0. We know that lines of force, you must have studied this in your high school, that lines of force come out through the north pole and they terminate on the south pole. Okay, so since a magnetic field is always solenoidal, so the number of lines of force that come out from the north pole will always go and terminate on the south pole. So magnetic monopoles can never exist, which is the reason, which is a consequence of the fact that a magnetic field is a solenoidal field. Whereas this is not the case for electric field. For an electric field, a single charge can always exist. An electron can exist by itself. A positive charge can exist by itself. The lines of force will come out and go up to infinity, or the lines of force from infinite distance can come and terminate on the charge. So there is no problem because an electric field is not solenoidal, but a magnetic field is solenoidal, which is why magnetic monopoles can never exist. Okay, so you can be given, short problems like you are given a vector and you are given a question like this. Uh, State whether this vector can represent a magnetic field. Okay, so you might think that I am writing a paper on vector analysis. Why is the teacher giving me a question on magnetic field? Because it is related. What will you do? You will quickly find the divergence of the given vector. If the divergence is 0, it means the given vector is solenoidal. And so yes, this vector can represent a magnetic field. But if the divergence is non-zero, then you can easily say that since the divergence is non-zero, so the given field is not solenoidal and therefore it cannot represent a magnetic field. Okay, so this kind of problem you can be given. You are given a vector field and asked to find out whether for this particular vector field, say whether it is a source or a sink or a solenoid. So you have to quickly find the divergence. If it comes out to be greater than 0, you say it is a source. If it is less than 0, you say it is a sink. If it is equal to 0, you say it is solenoidal. Okay, so this is the kind of problem that you may get from the physical significance. The derivation that I did in my last 2 slides, those are not required. You do not need to learn them. I just made those slides so that you can understand why the divergence of a vector is related to the flux of a quantity, and you will also need this when we do the integration theorem called divergence theorem. Okay, maybe in next class or next to next class. Quickly we'll do the last differential operator, which is the curl. So for a differentiable vector field v, x, y, z, the curl of the vector field is defined in this manner. Okay, curl of v, which means you write the form of the del operator, del x I cap plus del y j cap plus del z k cap. Take the cross product with v, v1 I cap plus v2 j cap plus v3 k cap. So all of you know the formula for the cross product, the determinant with I, j, k, del x, del y, del z, and v1, v2, v3. So this is the form of the curl. Clearly you can see that you have I cap, j cap, k cap. So the curl of the vector is a vector. Divergence is a scalar, but when you take curl, you get a vector. If curl of v is 0, if for any given vector you take the curl and you find that the curl is coming out to be 0, we say that the given vector is irrotational. So if you are given a vector and asked whether it is irrotational or not, what you have to do? You have to find the curl. If the curl comes out to be 0, you can write yes, this vector field is irrotational. We'll talk more about irrotational vector fields when we do integration theorems. Okay. So with this class, you now know the 3 vector differential operators: gradient, divergence, and curl. You know how to take the gradient of certain vectors, certain functions. Sorry, you know how to take the gradient of scalars. You know what is the physical and geometrical significance of gradient. We just did the divergence And I told you that the physical significance of divergence is related to the flux of a group of particles, of moving particles or magnetic lines of force. And you also know how to take gradient of a function of r and divergence of a function of r multiplied with the r vector. And finally, this is the form of the curl of a vector. So if any vector is given, you can simply use this formula and find its curl. For homework, I want you to find the curl of the position vector r, xi cap plus yj cap plus zk cap. Okay, and I'll ask you in the next class what is the result of curl of the position vector r. Okay, so in our next class, we'll start with vector integration. And I'll check what else is there in your syllabus. So I don't think we'll need, I think we'll need only 2 or 3 more classes to finish off, and then you can get ready for your exams in March. Okay, any questions from this class? Anyone has any question? If not,